Hello, namaste. Welcome to this channel Chemistry Made Easy by Dr. Ashok Mulik. Today we will see the Aufbau Principle. It is a part of this atomic structure. So, by this time we have seen the previous part of this topic, which is related to the various types of quantum numbers and the shapes of atomic orbitals, where there are also some other things such as the nodal surfaces or nodal planes, etc. Now we will see the next part, that is Aufbau principle. Under this point we have to consider that when the atomic structure is known to us, the quantum numbers are known to us, the various types of atomic orbitals are known to us, then we have to go further for distribution of electrons among various orbitals and energy levels, so that an atomic structure is developed. So this development of atomic structure with the distribution of electrons is very important thing. But when this electronic structure is considered for hydrogen atom, then it is very easy job, because there is only one electron for distribution in the atomic orbitals. So in this case we are considering the value of n is equal to 1, then L is equal to L is equal to 0 and L is equal to 0, and here we have to consider ms, spin quantum number, that is equal to -1/2. So this is easiest thing for hydrogen atom. This is for hydrogen atom. So it will show that the n is equal to 1 means first main energy level. L is equal to 0 indicates S subshell, that is S subshell, and ML indicates the shape of that subshell and orientation of that electron cloud in the space about the nucleus. Then MS indicates spin quantum number, that is -1/2. So this quantum number is usually represented in this symbolic form, that is arrow, half arrow we see with upward spin, and when we use downward arrow, this is having ms value plus 1/2. So upward half arrow indicates spin quantum number -1/2. Downward half arrow will indicate the spin quantum number plus 1/2. So if we go for other structures of atoms, then we have to follow specific rules, because around the nucleus in the given atom there is large empty space, which includes variety of energy levels and variety of atomic orbitals. But it is difficult to place any given electron, and therefore we have to follow some definite or well-defined rules. So we have to follow these well-defined rules in order to go for distribution of electrons among the available atomic orbitals with the help of these quantum numbers. So in this process we have to follow the suitable rules, and these rules are, so we say this is rule number 1. So for hydrogen atom we have seen that it is very easy, but for atoms, multi-electron systems, the distribution of every electron is very important thing. Then it shows that the electrons placed in orbitals to give the lowest energy possible. So we have to choose those orbitals so that energy, total energy of the system becomes as low as possible. So first rule says that distribution of electrons should result in lowering of energy of the system, that is atom. So lower the energy, more is the stable the atom. So lower the energy, stability of the atom will be more and more. And on the contrary, when the energy of the atomic orbital is higher, the stability energy of the total system after distribution of electron becomes higher. It shows that the atom is not more stable. So stability depends upon the distribution of electrons. So this means that we have to choose such a quantum numbers so that the atomic orbitals of lowest possible energy levels are occupied first, and we have to use the suitable quantum numbers, say that is N, L, ML and S. So these are important. MS indicates only what is the spin quantum number. So there are variety of atomic orbitals such as P and D. Here P has 3 sets of atomic orbitals. D has 5 sets of atomic orbitals. So these orbitals, if we consider these orbitals of P, then we have to consider that energy of these 3 orbitals is the same, that is called a degenerate. Similarly, energy of these 5 orbitals is also same, means energy of this orbital is equal to this in this way. So all these 3 orbitals are at same energy level. So these are also degenerate. So every atomic orbital having thus identical energy will show the suitable energy, or we have to consider the equivalence of energy of these orbitals while distributing the electrons, and thereby we are going to keep the lowest possible energy level of the system. Then the next rule is, that is second rule, is Pauli's exclusion principle. Pauli's exclusion principle. So this principle shows that whenever we have 2 or more electrons in the atom, whenever we have 2 or more electrons in any given atom, then we have to assume, or we have to be sure that all these electrons are defined by a set of quantum numbers which should indicate that at least one of the quantum number in each set for the given electron should be different. Means, in short, say first we have say 2 electrons, so we are considering 2 electrons. Then there are the specific value of N, L, M and S, ML and NS. Then for every electron, these 4 values should be different. Means the 2 electrons should not have all the 4 values of quantum numbers the same. All these 2 electrons should not have all the 4 values of quantum numbers the same, but at least one value of quantum numbers should be different. Then only the distribution of electron is correct. So it means the four values of quantum numbers are responsible to give correct address or location of the given electron in the space around the nucleus of the atom. So it is called Pauli's exclusion principle. Means we can state in this way that no two electrons in the given atom should have the same set of all the four quantum numbers. Means every electron or any electron should have at least one quantum number value different from for any other electron present in the atom. So if say the atom has say 10 electrons, so these 10 electrons will have 10 different sets of quantum number values, and every electron has at least every set of the quantum numbers for every electron should have at least one quantum number value different from other electrons. Then only the electron distribution is reliable. Then the third rule is that Wood's rule. So Wood's rule is considered for maximum multiplicity. It means when we consider the atomic orbitals having the same set of or the set of different atomic orbitals of similar energy. So for example, if we consider p orbitals, so these p orbitals have three different atomic orbitals. So these are, we can name as px, py and pz. So these three atomic orbitals are different from each other because of their orientation in the magnetic field is different, but their energies are same. So in such case, we have to follow this Wood's rule of maximum multiplicity. Now we have to see what is this maximum multiplicity. Say for example, we are having two electrons. We are having two electrons available for this distribution in these atomic orbitals. Then there is this one type of probability. There is only one type of probability. So this is say first probability. Then if we are having another probability like this, then these two electrons alternatively can be shown in this way. These two electrons can be alternatively shown in this way. Means the electron, in this case, the electrons are paired. So one electron has -1 half spin, other electron has +1 half spin. So that is called a pairing. So here, both these two electrons are not paired, but their spins are different. It has +1 half spin, it has say -1 half spin, and this has +1 half spin. So the total spin is 0. It has also total spin 0, and because of this, the distribution slightly differs because the two electrons are present in one atomic orbital. In this case, the two electrons are distributed in two different atomic orbitals. But here, in this case, spins are opposite. Here, in this case, also spins are opposite to each other. But now we can consider third situation in which both the electrons are of same spin. Here, the two electrons have same spin. Say this has minus 1 half, this has also minus 1 half. So the total spin of this is minus 1. Total spin is here minus 1. So here, according to this Woods rule, we have to choose that type of configuration in which the total spin is maximum. Here, in this case, spin is 0 means lower. In this case, spin is 0, total spin. But in this case, spin is 1. That is minus 1. So, do not consider, we should not consider whether it is negative or positive. We have to consider the total value. So, here, the minus 1 half means 2 electrons are present in the same type of spin. Means they are, say, either clockwise, they are in the spinning about their own axis in either clockwise direction or in other anti-clockwise direction. So here both spins are same. Now we have to consider that. So spin is, when the spin is 0 means spin is paired. When the spin is paired, the energy of the system is high and stability is low. Stability is low. Here also same case. In this case, spin is energy of the system is low and therefore stability of the configuration is high. Stability of this configuration is high. Hence, we should go for such a configuration in which energy of the system is lower and stability is higher. So we cannot go for these two types of configurations because the energies are higher and therefore stability of such configuration is lower. So that is not suitable for the given structure of atom. Here, multiplicity is given by, here we say multiplicity. So multiplicity is given by number of unpaired electrons. Plus unpaired electrons of like spin plus 1. So here you will find that in this case there are 2 unpaired electrons. Plus 1 means 1. So this gives 3. So 3 is the multiplicity of this configuration. So this configuration will have multiplicity 3. So if you consider the number of unpaired electrons here are 2, but they are in opposite direction, means their spins are not same. So these are having 0 multiplicity. So in this case, the multiplicity is calculated as, so this total spin or number of unpaired electrons of same spin are 0. Number of electrons in this unpaired electrons of same spin are 0. Plus 1 means multiplicity is 1. In this case, the number of unpaired electrons are also 0. Plus 1 means 1. So multiplicity here in this case is 1. Here it is also 1. But in this case, the multiplicity is 3. So such configuration having maximum multiplicity is preferred over the less multiplicity. So multiplicity is the number of possible energy levels that depend on the orientation of the net magnetic moment in the magnetic field. So any arrangement results in favor of or in fewer electrons. This is considered here. So we will consider some examples in which the electronic distribution can be understood easily. So if we are considering, say, number of electrons in the first column, then we will see the arrangements of electrons, and third is the unpaired electrons, and the maximum multiplicity, that is multiplicity is multiplicity. So here, when we are having say only one electron, so when we have only one electron and the arrangement is considered for 3 atomic orbitals, so we can consider here, for instance, these are p atomic orbitals, that is px, p1, p3. Then we can have the distribution of electrons in this way. So out of these 3, any orbital can occupy this available electron. So we can show this electron either here or here or here, anywhere we can show. But for our regular consideration, we are choosing first atomic orbital. All these 3 are equivalent in energy, that is degenerate. So we can place this electron in any of these 3 available atomic orbitals. Then the number of unpaired electrons are 1. Multiplicity is calculated as number of unpaired electron plus 1. So multiplicity is 2. Then when we are having say 2 electrons, then we can show the distribution like this. So these 2 electrons are to be placed with same spin. Then in this case, the unpaired electrons are 2, so 2 plus 1 is 3. So multiplicity of such configuration is 3. Now we will see the third electron. So these, when we have 3 electrons, then the distribution will be like this. So these 2 electrons will go in this way. So each atomic orbital of same energy will occupy one unpaired electron with the same spin. So spin states are same. There should be no electron with opposite spin. Every electron should have like spin. And therefore such electrons are counted here as unpaired electrons. Unpaired electrons are 3 and plus 1 gives multiplicity, that is 4. So here another, when we are having 4 electrons available and the atomic orbitals available are like this, then we can show the distribution like this. So out of these 4, 3 electrons are distributed in this way with like spin. Then if we are having 4th electron, it will go into any of these 3 orbitals with opposite spin. So we can place that 4th electron here or here or here. So for our convenience, we are showing here. So after this, we are having how many number of unpaired electrons? 2. And plus 1 gives multiplicity 3. So the multiplicity gets reduced because the number of unpaired electrons are reduced. Then we are having 5 electrons with these 3 energy orbital, atomic orbitals. Then the 5th electron will go like this. So these are 4 electrons as shown above. So to this, when we add one more electron, that is 4th electron, it may go here or here. So each atomic orbital can occupy a maximum of 2 electrons with opposite spin. Here, when atomic orbital is only 1, then it should have 2 electrons with opposite spin. It may have also 1 electron when there is only 1 electron available. Then, when we are having 6 electrons, so we have to show here these. So the 6 electrons are shown here. So first 3 electrons will go with same spin. Next 3 electrons will go into each orbital with opposite spin. Now in this case, the number of unpaired electron is 1 plus 1 gives 2. And in this case, number of unpaired electrons are 0 plus 1 is 1. So in this way, multiplicity varies with the number of unpaired electrons available. So this rule is a consequence of energy required for pairing of atomic orbitals. Now what happens with the energy? Energy of the system, or we say here we are finding pairing. So pairing of electron requires more energy. So pairing shows involvement of more energy, and unpairing shows involvement of lower energy. So this pairing or unpairing, here you will find all the 3 electrons are paired. So the system is showing more involvement of energy. So consequence of this energy required for pairing in the same orbital. When 2 electrons occupy the same part of the atomic orbital like this, it may have both electrons with opposite spin. Then when 2 electrons are there, both electrons are negative in nature, or any electron has negative charge. And when 2 electrons are coming closer, what will happen? These electrons will repel each other. So the energy associated with this repulsion is called the Coulombic energy. So this is called Coulombic energy. And this is indicated by pi c. So here you will find that in this case the Coulombic energy is more, and therefore the system shows repulsive forces, and because of this configuration is becoming more and more unstable. So there is also, in addition to this, there is some exchange energy. So what is exchange energy? When we have 2 electrons, and the atomic orbitals are like this. Say we have 2 electrons and we have these 3 atomic orbitals, say p orbitals, that is px, py, pz, etc. Then we are having, say, if 2 electrons, then we can show the distribution like this. So these 2 electrons can be shown in this way. Out of this is the first case. So we say this is first case in which both the electrons are paired in state. So the pairing is shown here in one atomic orbital and keeping the 2 atomic orbitals empty. So this is first condition. Then we will see the second condition, in which the distribution of electron is slightly different. So here we have to consider that the 2 electrons are placed in this way. So the 2 electrons are placed in this way, in which the spin states are opposite, but the 2 electrons are placed in different atomic orbitals, and we know that this is px, say this is py, and this is pj. So the 2 electrons are placed in different atomic orbitals. Here in this case, 2 electrons are placed in the same atomic orbital. So this is second case, and in the third case we find that so we are having, say, these 2 electrons with the same spin. These 2 electrons are having same spin. So here in this case the Coulombic energy is more because the electrons are paired. In this case there is only possibility of exchange energy, and this is lower energy, this is lowest energy, this is relatively higher energy, and this is more higher in energy. So we will see this here. So if we consider this energy axis, then we will show that the energy difference between these two atomic orbitals, A levels, we will see this level and this level is pi c, that is Coulombic energy. And when there is these two types of atomic orbitals available, then the energy difference between them is called pi e, that is exchange energy. So here, what is exchange energy? So that can be explained here. So we will explain this exchange energy. So consider these three options where this electron, so these are two electrons. For our convenience, we will label these electrons as electron number 1 and electron number 2. Means we are labeling these electrons in order to understand the exchange energy. Now we will have another alternative distribution like this. So the electrons are same as per its size, shape, charge, etc. But in order to distinguish between the two electrons, we have labeled as one atom. Now in another option we have shown that this is second electron and this is first electron. Now you will understand that this electron number 1 is placed here in this set of atomic orbital. But this electron is coming here and this electron is going in the first atomic orbital, that is px. So here px has one electron number 1, but this electron number 2 goes into py in another. So this is called exchange. So this 2 comes in the place of first electron and this number 1 electron goes into second place. So this is exchange of electron and this will require some energy, and that is called exchange energy. Exchange energy, and this is represented by pi e. So pi e represents exchange energy. So in this way we can have